Gravity and Projectiles by Henna Parmar. So first I'm going to start off with an explanation of what gravity is. Gravity is a force that pulls an object's center towards another object's center. The larger the object's mass, the stronger the gravitational pull is. Earth's gravity is what keeps things held to the ground, otherwise everything would just float away. Earth's gravity is what causes things to fall. Gravity is what holds the planets in orbit around the sun. Gravity is also what holds the moon in orbit around the Earth. The closer the two objects are, the stronger the gravitational pull is. Gravity is what gives items weight. Next, I'm going to give an explanation of the equation for the universal law of gravitation. Isaac Newton first discovered the universal law of gravitation from observing an apple falling from a tree. He wondered why the apple never dropped sideways, upwards, or any other direction except in a straight path downward. He was then able to construct a general physical law by observing his surroundings. The universal law of gravitation states that every body of mass attracts itself to another body of mass in the universe by a force. The force is in a straight direction between the two centers of masses. The force of gravity acting between two objects is directly proportional to the masses of the objects and inversely proportional to the square of the distance that separates the centers of objects. This law applies to all objects with mass. Newton's law of universal gravitation extends to gravity beyond Earth. His law is about gravity in all corners of the universe. He did not just discover gravity, but also the fact that it's universal. Since the gravitational force is directly proportional to the masses of both objects, the bigger object will attract the other with a greater gravitational force. If the mass of either of the objects increases, so does the force of gravitational attraction between them. Knowing this, Newton was then able to construct this formula: force equals mass times acceleration. Although Newton was able to come up with the law of universal gravitation and verify it, he could not calculate it. It wasn't until Henry Cavendish that the universal law of gravitation received a gravitational constant. This final formula is the equation for universal law of gravitation. Next, I will be using the equation for the universal law of gravitation to explain why acceleration near the surface of the Earth is 9.8 meters per second squared for all objects. The acceleration which is gained by an object because of gravitational force is called acceleration due to gravity. If you have two objects of different weight and drop them, they would reach the ground at the same time. The reason for this is the more massive the object is, the harder it is to move, so it ends up moving at the same acceleration. This is true for all free-falling objects. They all accelerate at the same rate due to gravity, unless air resistance affects one object more than the other. Isaac Newton worked out that force equals mass times acceleration. The larger the mass of the object falling, the larger the force of gravitational attraction pulling it towards Earth. Force equals mass times acceleration. In this equation, this is force. However, this amount of times the force gets larger or tinier is equal to the number of times the mass gets larger or tinier. Therefore, the ratio remains the same every time. In every situation, the force and mass cancels out, leaving the acceleration of around 9.8 meters per second. This means that regardless of their masses, all objects in freefall accelerate at the same rate. I will now be talking about the shape of a projectile's path. A projectile is an object with the only force acting on it is gravity. Many projectiles have a vertical motion and a horizontal motion. That means as they move up or down, they are also moving horizontally. These two components of a projectile's motion are horizontal and vertical motion. These two components of motion are independent of each other. Consider an object projected horizontally from the top of a very high cliff. In the absence of gravity, the object would continue its horizontal motion at a constant velocity. This constant is the law of inertia. Also, if the object was dropped from a resting position with the presence of gravity, that object would accelerate down, gaining a speed at the rate of 9.8 meters per second. If the object is projected horizontally with the presence of gravity, then the object would have the same horizontal motion as before, a constant horizontal velocity. In addition, If the force of gravity is acting upon the object, it will cause the same vertical motion as before, a downward acceleration. The object will fall the same amount of distance as it did when it was dropped from a resting position. However, the existence of gravity does not affect the horizontal motion of the projectile because the force of gravity is acting downward. There must be a horizontal force to cause a horizontal acceleration, and it is known that there is only a vertical force acting upon projectiles. The vertical force will act perpendicular to the horizontal motion and will not affect it since it is perpendicular. Components of motion are independent of each other. Thus, the projectile travels with a constant horizontal velocity and a downward vertical acceleration. This in turn creates a curved shape. Now suppose that our object is directed up and projected at an angle to the parallel of the cliff. Without gravity, the projectile would travel along in a straight line. An object in motion would stay in motion at a constant speed in the same direction unless a force acted upon it. This would be the case for an object moving through space in the absence of gravity. If there is gravity, the object in question would be a projectile. In fact, the object or projectile would follow a parabolic trajectory. The downward force of gravity acting upon the object would cause the same vertical motion as before. The object would fall the same amount of distance every second as it did when it was dropped from rest. Again, the existence of gravity would not affect the horizontal motion of the projectile. The projectile would still move the same horizontal distance each second as it would if there were no gravity. Now I'm going to do a sample projectile motion problem. For this problem, we will be finding the height at the apogee, the downrange distance, the time in the air, and we will be given the initial velocity and the launch angle. The initial velocity will be 10 meters per second and the launch angle will be 36 degrees. The first thing I'm going to do is draw a picture of the projectile. So we're finding the height at the apogee, the downrange distance, and the time it takes. And over here I'm drawing the initial velocity and the launch angle. Okay, so here I'm redrawing the triangle from the other picture. And we will use this to find the initial horizontal velocity and the initial vertical velocity. And we can use sine to find the initial vertical velocity. And the answer is 5.88. And we can use cosine to find the initial vertical velocity. So the answer is 8.09. After that, we are going to find the time. So we are using this equation. Now we're going to use the quadratic formula to find the time. So we end up with two answers, 0 and 1.65, and the time in the air is 1.65 seconds. Next, we're going to find the height at the apogee. And we are taking half the time and putting it into the equation we used before, because at half the time it was at the highest point, so that is why we can do that. And it's 3.38 meters. That was the highest point. Now we are finding the downrange distance. And the downrange distance is 9.7 meters. Okay, now I will be explaining how projectiles are related to satellites. A satellite that is orbiting uses the force of gravity. Most Earth satellites are orbiting at a distance far enough above the Earth that their motion is unaffected by air resistance. A satellite is considered to be a projectile. The force acting on a satellite is gravity, and gravity keeps the satellite in Earth's orbit. Without gravity, a satellite would move in a straight direction. Gravity acts on a high-speed satellite to diverge its trajectory from a straight path. The satellite accelerates towards Earth because of its gravity. The satellite falls towards Earth, but it never falls into Earth. Earth is round, meaning the surface of Earth is curved. When launched, the satellite falls towards Earth with a trajectory that matches the curvature of the Earth. The satellite will fall around Earth, always accelerating towards it because of the presence of gravity, but it will never collide into Earth because it is constantly curving at the same rate. If launched at a too fast speed, the satellite will outrun Earth's gravity and continue without orbiting the Earth. This is the very same actions of a projectile. Now I will be explaining orbital motion. Earth and many celestial bodies like asteroids, comets, and planets revolve around the Sun in curved paths called orbits. The orbits are usually elliptical or oval in shape. The four main types of orbits are hyperbolic orbits, spiral orbits, elliptical orbits, and circular orbits. Because of the Sun's gravitational pull, Earth and other objects constantly fall towards the Sun, but they remain far enough from the Sun because of their velocity, causing them to fall around the Sun instead of crashing into it. They continue orbiting the Sun and never crash into it. The motion of Earth and celestial objects revolving around the Sun is called orbital motion. Orbital motion occurs whenever an object is moving at a constant velocity while at the same time being pulled by the gravity of another object. Circular orbits occur when smaller objects' mass, velocity, and distance is equal to the larger object's gravitational influence. Circular orbits are the simplest kind of orbits. This is because an orbiting object stays at a constant radius as it travels around an object with a gravitational pull. No orbit stays perfectly circular, since every object is constantly being affected by the gravity of every object nearby. However, when an object like a satellite, asteroid, or moon orbits a larger object like a planet or star, it's a good estimation to treat it as a circular orbit. An elliptical orbit is stable, but has a tilted balance between an object's velocity and orbital distance. A longer, more peculiar orbit means that the object's distance and velocity is slightly overwhelming the gravitational pull. A shorter and fatter ellipse means that the scale is tilted more towards the gravitational influence of the larger object. The next type of orbit is a geosynchronous orbit. Geosynchronous, broken down, is geo means Earth, syn means same, chrono means time. Orbits of planets or orbits of objects going around planets will move quicker if it is closer to the object, and something is farther away will take a longer time. An object orbiting around the Earth exactly every 24 hours is said to be in a geosynchronous orbit. Most communication satellites are in a geosynchronous orbit.